Okay, so let's start with a quick review of what we did in the last class. Um, let's start with the singular value decomposition. Before that, how was the quiz? Difficult, easy, medium, medium? It was okay. Anyway, we'll discuss the solution next week. The TS will, or I myself will discuss the solution. And then I will hand over the evaluated uh, answer scripts. Okay, so let's get started. Quick recap. So last class we looked at a very important concept in linear algebra, very useful in many domains, especially data analysis, which is called the singular value decomposition. It's very important because of several reasons. Of course, it has a lot of use cases because unlike eigenvalue decomposition, there is no condition under which you can decompose this way. You give me any matrix A, I can write it as product of three matrices, right? U and V being unitary matrices, right? That means U Hermitian is U Hermitian U, which is identity. That means all the columns are orthonormal, all the rows are also orthonormal. That's what it means. And sigma being the diagonal matrix with diagonal entries being non-negative, it's greater than or equal to 0, and they are called singular values. Okay, and we related the singular value decomposition to eigenvalue decomposition. How do you find singular value decomposition using eigenvalue decomposition? So one way is you look at A Hermitian and A Hermitian A, do eigenvalue decomposition. You will get the corresponding matrices. The matrices that you get correspond to the left and right singular vector of this. So okay, that is another terminology. So for example, if you look at this, right? So the U matrix, the columns of U matrix is called the left singular vectors. Okay. Of course, for eigenvalue decomposition, we call it as eigenvectors. So here we call it as singular vectors. Okay. So obviously the columns of V, we call it as the right singular vector. And U is called the left singular matrix. V is called the right singular matrix. Okay. Yeah. Then I think after this, we started looking at principal component analysis, but we will revisit that again today. Okay. So let's get started here. Okay. So let's start with what is known as principal component analysis. So let's look at the setup. The setup is as follows. So you have data, you know where the data comes from, right? For example, you're doing spam versus non-spam classification problem. You take an email, convert it to a big vector called feature vectors, right? So that's what I call as data. So either that feature vector, or if you have a label for it saying spam or non-spam, I will call that set as a data set. Okay, so for example, you have x1, x2, etc., xn. Let's say it belongs to, or D is the dimension of your feature vector. That means you are considering D features to convert basically to extract the feature. Okay, so you are looking at D features here. Okay, so you have this data. So typically, in many applications, this D is very large. For example, if you look at spam versus non-spam, you collect all the bag of words, right? And then count the number of words, each word appearing in a text. So that is what you do typically in your NLP sort of problems, right? Natural language processing. So that D, for example, if you consider 20,000 words, then D will be 20,000, right? Huge. Okay. And that means if you look at X1, there are 20,000 numbers, and you have to do, if you want to do some data processing or data analysis, then you will be doing 20,000, you'll be dealing with 20,000 numbers. In many other cases, D is much larger. So we want to somehow reduce this for computation purposes, right? Without losing any information about the task. So what is the kind of problem that you will solve here? So essentially, think of, obviously I cannot write these points in n dimension or d dimension. Think of it as higher dimension, very high dimension. Now I want to reduce it to a lower dimension, right? So what are the ways and what kind of problems you will solve? Okay, so let me look at an example. Suppose I look at 3 dimension. Okay, so let's say 3-dimensional space, and you have let's say 1,000 points, right? What might happen is, these all 3,000 points could be on a plane, right? So all these, okay, maybe some of them are slightly above, some of them are below, but roughly on a plane, right? So supposing this is the case, do you really need to deal with 3-dimensional space? No, right? So if I think of this plane as, obviously a plane is a 2-dimensional space, right? So if I can somehow think of those points lying on a plane, then I, essentially by doing appropriate transformation, I can think of these points as 2-dimensional, right? Without losing any information, right? So now the question is, it's easier to say by looking at diagrams, but how do you convert that into math, right? That's the question. So now, what do you think you do? So essentially, what you end up doing is you have to project onto a subspace. Okay. Before that, a small aside. Um, for example, in 2 dimension, this is a subspace, right? A line passing through origin is a subspace. In general, any plane passing through origin will be a subspace. But what about this guy? What is it called? What I'm going to do is I'm going to take a subspace, give a small kick, right, in some direction, so it doesn't pass through the origin. How do you write this, by the way? So what is it that you are doing? So every point, for example, if I take this vector as let's say u, or u, all that you are doing is you are taking every point and adding a vector u to it, right? So you take every point here and add a vector u to get this, right? So how do you write it mathematically? This is, let's say, vector space V. It's a subspace. What is this space? It's V plus U, right? Which is set of all V plus U such that V belongs to V, right? That's all. What is this called? Do you know? Any idea what this is called? The name. So what kind of a transformation is AX plus B or A something plus B? It's called affine. Okay, so this is an affine set. Okay, anyway, this is just a name. So in other words, you take any plane in n-dimensional space, it's either a subspace or it has an offset. Okay, so now you have these points, right? All these points. It may not lie on a plane, it will be around a plane, right? But I have to approximate it by a plane. So what do? So this is the problem that I would solve, right? So first of all, I want to project it onto some subspace or some space, right? So that means each point xi I take, which is d by 1 vector, right? D-dimensional space. I project it onto some space P, Px. So P is a matrix, which is, let's say, some k by d. K is something that I'm going to fix beforehand. Let's say you have some idea of how the data looks like. You know that it's on a plane in some k dimension. You have some rough idea based on the physics of the problem. So now I want to bring it down to k dimensional, not d dimensional, right? So obviously d is much larger than k, right? This is the assumption. Otherwise, it makes no sense, right? If it is 10,000 dimensional space, you are projecting it onto 9,998 dimensional space. Doesn't make sense. Okay. So now you have Pxi, right? Now, if you look, so this Pxi will project onto some subspace. It can be anything, right? For example, it can project onto 3-dimensional subspace or some other 3-dimensional subspace and so on. But I want this to be as close as possible to xi itself. If you go back, for example, you have a point here on this plane, and if your projection is P corresponds to projecting onto this plane, this point is same as Pxi is same as xi, right? It will lie on that plane itself. So the distance is 0, right? Norm difference is 0. But if it is here, for example, all that you're doing is projecting it here. I mean, you're just looking at the closest point, right? So what I have to do is I have to look at the difference, and I have to take, let's say, norm squared, right? Well, I won't look at uh, yeah. So this is did I do this correctly? It's k by, this is d by 1. I want this to be as close as possible to uh, there is a mismatch, right? So this would be k by 1, right? Should be k by 1, and this would be d by 1, right? So there is a mismatch here. So how do you fix it? So you project, and you want that projection to be same as xi, right? How do you do that? Okay, so let's modify a little bit. So this doesn't work, right? Dimension mismatch. So what I'm going to do is I'm going to ensure that this is I want d by d, right? So I'll keep it d by d itself, so that the dimensionality mismatch won't happen. But now there is an issue, right? So for example, if you project, right? So p is a projection. Now, if you sum it over all I, and I want to minimize over all p, right? So clearly p is identity. That's the solution for this, right? If you make p equal to identity, then xi minus xi 0, right? You'll get the minima. But I want to restrict my p in such a way that this pxi, although it appears as if it's in b cross 1, I want to make sure that some of the values can be ignored, right? So subject to some constraint on, what do you think is the possible constraint here on p? What are the possible constraint on p? Huh? What are the possible constraint on p? Yes, any idea? What do you think is this p should be? Huh? Okay, so we can say, for example, rank of p should be less than or equal to some k, right? So fine. Anything else that you can think of? Right? In that case, well, it's not straightforward, right? So what do you do in PCA? This is an optimization problem, which well, it's a hard problem, right? It's very, very hard problem, because we will see why, especially because of these rank constraints. Ranks are hard to deal with, right? So what do you do in PCA generally? Let's look at that first, okay? And we will see why we do that later, okay, once we start studying optimization. So what is it that you do in PCA? The first thing that you do is you construct what is known as the covariance, right? So what is the covariance? This is what you do, right? I equal to 1 to n xi transpose, right? xi transpose will give you the covariance of, I mean, just one sample estimate of the covariance. So how do you estimate? For example, I give you a coin and I ask you to find the bias of the coin. What do you do? How do you estimate? You toss the coin n times, take n samples, average them, right? If I ask you to find the variance, what do you do? What is it that you will do? Yes. How do you find the variance of a coin? Probability question, but how do you find the variance of the coin? Any idea? Yes. Variance of the coin. What do you do? First, you find the mean, and then you look at each sample, subtract the mean, square, add them up, and divide by n, right? That's what you do, right? If it has zero mean, suppose I give you n samples, it has zero mean. How do you find the variance? You square them, add them, divide by n, right? Because the mean is zero. Now, how do you find covariance? See, covariance is what? Expected value of XX transpose, right? There's an expectation here. I'm finding the average of this matrix, right? I'm going to sample X from some distribution. I'm looking at the average of XX transpose. Now I don't know the distribution of X. So what do? I have samples, n samples. I'll take each sample, Xi. I'll take Xi, XX transpose, that gives me a matrix, right? That's an estimate of your covariance, right? One sample estimate. And I can do n such things. I add them and divide by n. Okay, this is assuming zero mean, right? Okay, so what do you do after that? What do you do after this? Okay, so the second step is you have the covariance now, right? If the mean is not zero, you can estimate the mean and subtract, and you say xi minus mu I hat times xi minus mu I hat whole transpose, right? And sum it over all I and then divide by n. Okay, so now what is the next step? So typically I should look at in which direction this S has the highest component. Okay, so how do I do that? I take S and project it onto both the directions. So basically I will do this. Okay, so V transpose S V. I want to ensure that this direction doesn't depend on the magnitude of U. I will constrain it to be unit norm. Okay. What is this saying? See, if you look at xi transpose, right, on an average, I'm seeing what does this xi points to, which is the direction which has the largest component, right, for each xi on an average. That's what I'm trying to figure out here. Is that fine? Do you agree? So, for example, in the previous case, this is the direction in which probably you have the highest component, right? The other direction is this. The third direction is you should not consider because the components are very less. Maybe I'll throw it out. Right, even if there are some component along the y direction, whatever this direction, the values are so small that I'll ignore, right? That's what I'm trying to do. So what do you think is the solution of this? What is the solution? Guess. Of course, I haven't taught you how to solve this problem, but roughly I have mentioned, right? So what do you think? In fact, I have shown what the solution is. What kind of a matrix is S? What is the first thing that comes to your mind? S is square. Okay, fine. D cross D, right? Yeah. Second, positive
semi-definite.
Positive semi-definite. Good. Then, okay, it's a square, positive semi-definite. What else you can say? It's symmetric also, right? S is S transpose. Symmetric. So you have eigenvalue decomposition. So what does this correspond to? So the solution V star is V1, right? Which is the eigenvector corresponding to the maximum eigenvalue of S, right? So this is the eigenvector corresponding to max eigenvalue, right? This is something that we saw, right? I mean, if you project it, you better align it to the max eigenvector, right? So I got the direction V1, right? Right. So I take the data and I'm going to project every data point onto V1. So what does that give us? It gives us one-dimensional approximation of the data, right? So it's just one dimension. Do you agree? Right? I don't need to consider what is the importance of that. Well, every data point in that one dimension, I can write it as some alpha times V1. So I need not deal with d entries. I only have to deal with one number, right? Alpha, right? What is the scaling? Do you guys understand this? I mean, why this is dimensionality reduction? Although if you looked at here, right, when I wrote k cross d, I mean, it's not really k cross d, right? So there is a dimension mismatch. But why should one project onto a plane and see? It's simply because what? I want to ensure when you look at two dimension, right, in let's say large dimension, all that I need is two vectors to describe that. These two vectors are fixed. All that I need is two numbers to describe all the vectors there, right? The moment you fix the basis. That's why it's interesting and useful. Okay, now what is the next step? So you have V1 corresponding to the max eigenvalue. So what will be the next step? Let's say if you want rank 1 approximation of your S, right? Sigma, so look at the max eigenvalue, lambda max V1 is one rank 1 approximation of S, right? What is rank 2 approximation of S? I have to consider both, right? So what will be the problem that I'm going to look at? Again, the same thing, V transpose SV. I want to maximize overall V subject to, of course, I want this V to be unit norm. I cannot stop here, right? At the moment I stop here, I'll get the same solution as before. What should be the second constraint? This should not be in the span of V1, right? I have already found out V1. So it should be, right? It should be orthogonal to V, right? The reason why I'm saying all this is, you should be able to understand how to pose a problem, right? In data analysis rather than just solving it. That's what optimization teaches you, how to solve it, right? So what do you think is the solution of this? V star is V2, right? V2 is what? The eigenvector corresponding to the second largest eigenvalue. Well, we will study optimization. We will understand how to get these things in a formal way using optimal, whatever, duality principles. But for now, there are other ways to prove, right? You can use eigenvector eigenvalues to prove this, right? So you got this, right? What is rank 2 approximation of the matrix? I mean, if you want to just look at two-dimensional, you want to come up with a two-dimensional space where you want to say most of the data lies, it's basically V1, V2, right? Span of V1, V2, or along the direction lambda 1, V1 and lambda 2, V2, right? These are the directions. It has the maximum component, right? So what will be the, let's say, ith solution? You just do this, right? Again, you do max overall V transpose SV subject to norm of V is 1, and instead of V1 transpose V equal to 0, you say Vi or Vj transpose V equal to 0, J equal to 1, 2, 3, etc. I minus 1, right? Because the ith step. This is the ith rank approximation of the matrix, right? So you are looking at I-dimensional subspace, right? This is how you do. This is essentially principal component analysis, right? What is principal? It's like main or important component, right? The first important component is V1, the second important component is V2, and so on. That's what we have looked at here. Okay, is this fine, everyone? Right? Well, what is the solution of this? Well, the solution here would be Vi, right? This is the solution. Okay, right? Okay, let me ask you one more. Any questions? I can pause for a minute. We will look at the next problem. I'll ask you to propose a problem rather than solving it. Okay.
Sir? No, sir?
Yes, yes.
Sir, why is V transpose V 0? Can you explain that again?
V1 transpose V, right? See, you have already found out the first principal component, which is V1, right? If you don't consider this constraint, then it falls back to the previous problem. You will always say V1, right?
Okay, got it.
So I want it to be in the orthogonal direction. It should not be in the span of V1, right? And similarly, the fourth optimization problem, it should be orthogonal to both V1 and V2. In other words, you should not be in the span of V1, V2, right? And so on. Did I answer your question?
Yes, sir, yes.
Okay. Any other questions?
Sir, do we first calculate the eigenvalue and vectors and then propose this max V transpose SV?
No, basically the intuition is first problem or this particular problem says basically we are trying to find what is the principal component here, right? The first principal component. It turned out to be the eigenvector, that's all. So essentially, in doing this process, you figured out that the eigenvalue decomposition is very, very important. Okay,
Yes,
is
sir.
that fine?
Yes, sir. So suppose if I try to approach this problem this way, that I find the way that we find normal eigenvalues and vectors, and then choose suppose the first one or two eigenvalues which is greatest among them. So will this
Exactly.
work?
Yeah. So essentially, if you have this S matrix, I ask you to find, let's say, the rank 3 approximation of this particular matrix. It will be something like this. This will be the rank 3 approximation of this matrix. Okay, rank 3. That means among all possible matrices of rank 3, which one will have, which is in some sense closest? The answer turns out to be this particular matrix. Okay, of course, you have to match the dimension, you have to put zeros for others. That's a different thing. But apart from zeros, this will be the match. Is that fine? So I can always stack zeros and complete the matrix, right? So it doesn't matter. Is that fine?
Yes, sir. Thank you, sir.
Okay. Yeah. So essentially, let's look at another problem now. Okay. So this is problem 2. Right. So let's say I want to classify things, right? If I want to classify, for example, let's say now let's look at reducing things itself. So now let's say you have one class which is class A, right? And you have another class which is class B. And these are the points that are labeled, and it's in very high dimensional space. Again, D is very large. Now I don't want to deal with, let's go back to the original problem of, I don't want to deal with D numbers. So what do? I bring that down to lower dimensional space, right? I'll also bring this to lower dimensional space. Now I have to bring this to lower dimensional space in such a way that, of course, I have to use the same matrix to bring it down. Okay, same projection matrix. But I should ensure that even in the lower dimensional space, I should be able to classify them, right? So what do you think is the problem that you will pose? Let's say you have these data, right? So x1, this is the data. Okay, so I'll write the problem clearly. So this is the data: x1, y1, x2, y2, and so on, xn, yn. So yn can be, or yj can be either -1 or 1. Think of -1 as spam and 1 as, or -1 as non-spam and 1 as spam, or any classification, right? So if this is the case, these are called labels, right? And this particular learning procedure is called supervised learning. So now given x1 through xn, right? So I want to project it onto lower dimension, yet I should be able to find, make sure that they're far off. So how do you ensure that this is achieved? What is the problem that you will solve? Or okay, so I'll also say yj could be in R if you are looking at some regression problems, right? You might be looking at some regression problem like house pricing and so on. It doesn't matter. Okay, so now how do you find, what is the problem that you will pose? What is the problem? How do you do that? So if they are far here, right, these two things, you should remain far here also, right? So how do you ensure that? How do you ensure? Yes, how do you ensure that if they are far in the higher dimension, when you go to the lower dimension, it should be far again? So what do you think is the problem that you will pose? Huh? Same norm. Meaning? So, for example, you take this to this, right? So, how do you do that? Suppose this is x. What is this? How do you represent this? This is d dimension, right? There are d numbers. Now I have to go down, right? So what should I do?
X.
Yeah, px, right? Px will give me lower dimension. So if x is d cross 1, this should be some k cross 1, say k cross d, right? So it will be k cross 1. So k is much smaller than d. Okay, fine. So now what is the problem that you will solve? So you know how to bring everything down, right? But how do you ensure? What is the problem now? See, one thing that I have to ensure is if you look at 2 points in different classes here, when you project it, the distance should be maintained, right? It should be as large as possible, right? Do you agree? And within the cluster, right? If you take these points within the cluster, it should maintain distance, right? That's what you want to do, right? So how do you pose that as a problem? What do you think? What do you think if I want to solve this problem? What kind of problem should I write so that I can hope to solve in this course? What is it that I have to do? What is it that I have to do? See, first of all, I look at two things, right? So p xi is the ith data point, p xj. Now, suppose I and j belong to the same cluster. For example, both are spans. What is it that you expect? What should be pxi and pxj? These two are vectors in lower dimension, right? It should be
Close to each other.
close to each other, right? If they are from different, it will be far off, right? So essentially, how do you measure closeness? To 2 now. Maybe I'll take square also, right? Square is easy to handle, right? Okay, now this is among two nodes, two data points, xi, xj. Now, if you look at, for example, the distance across, right? I should ensure that they are far off, but within they should be close, right? So what should I do? I should sum over all I. You fix a j, okay? J in some cluster, and I is in some other cluster. So if you fix j, I should sum over all possible i's in the other cluster. So let me call this as cluster 1. Okay, cluster 1 is, for example, 1, 2, 3, 4 till 10, and I should sum it over all j cluster 2, right? It will give me the sum of the distances across all possible points, across the two clusters, right? Do you agree? Right? In practice, people won't do this, but this is one way of posing the problem. Now, I want to ensure that this is as large as possible, right? So I have to figure out a matrix P such that it's as large as possible, right? Separation. But what should I do? Of course, I can always do by, I don't know, many things, right? So what should happen to the inter within the cluster? It should be small, right? How do I write that? So again, you look at, I'll write a different one. I'll say pk and maybe I'll use lm. Okay, pl, pxl, pxm. This distance should be as small as possible, right? I'll say less than some delta. This should be true for all to C1, right? And for all Lm belonging to C2. Okay. That means L and M you pick from one cluster, it should be very close to each other. If you pick Lm to the other cluster, it should be close to each other, but across it should be as far as possible, right? This is how you come up with a problem. Then you stare at it and say we can simplify and do something else, or maybe you can come up with an algorithm which is heuristics and see what is the performance of this. So many things can be done, right? A good problem is half the solution, right? So you should come up with a good problem first. Okay, is this fine? Okay, And of course, you can post several other. So let me look at one more, which will sort of motivate few things. So suppose I give you, this is like a linear separation problem. So, so suppose I give you two data sets, okay, something like this. Right? How do you separate? Well, straight line, right? Of course, you can also use curved lines, but straight line is the most obvious, right? In n dimension, it's a hyperplane, right? That's how you separate out, right? Now, what are the questions that we can ask? Suppose I throw data like this at you, let's say 10,000 dimensional data points. You cannot plot and see whether you can separate, right? So what is it that you have to do? You have to mathematically verify whether it is separable by a hyperplane, right? So the first question that we can ask is, are the data points separable by a hyperplane? We will see what a hyperplane is. What is the next question? If so, the answer to the first question is yes. Then how do you find that hyperplane, right? If so, how do you find the hyperplane? Well, I think in the first class itself, I came up with a problem which is straightforward, intuitive, but that's not how you solve this problem, or that's not how you pose the problem. Also, it's very. I looked at indicator function as losses, and then we pose this problem as a minimization of losses with respect to the parameters of your hyperplane, right? Find the hyperplane. So in both the cases, you came across this word hyperplane. Let's try to understand what a hyperplane is, because this will be very, very important throughout. If you look at any optimization, hyperplane plays a very, very important role, even in duality theory. So let's look at, let's take this opportunity to understand what a hyperplane is. Well, hyperplane is a plane in higher dimension. That's all. So what is a plane in higher dimension? How do you describe a plane? Suppose I give you this. It's a plane, right? So how do you describe this plane? Of course, let's say everlasting. It's not, although I have written a box here, it extends to infinity. So how do you write a hyperplane, or mathematically describe a hyperplane, given that you have learnt linear algebra? What are the two ingredients? So if I have to, suppose, let's say there is a contest wherein I have to give little information, but you should be able to write the hyperplane that I want to write. So what is that little information that I should give you? First thing is the point, right? So at least I need one point through which the hyperplane passes, right? For example, a line, if I want to describe line, Euclidean geometry, right? Euclid wrote that 2000 years ago. You need 2 points, right? That's all. But in general, if you look at hyperplane, 2 points are not enough, right? I can have infinitely many planes passing through the 2 points. So what else you need? Let me call this point as some, I don't know. Okay, let me rename it. Let me name it later. Okay, maybe you. Okay. What else you need? You need a perpendicular to the plane, right? At this point. Let me call this perpendicular P. Okay. Well, the perpendicular is, well, this P is not from, this is not P. Okay. So this is like the vector joining U and this point is, or the direction in the perpendicular direction at U is called P. Okay. So P is, let's say, a unit vector. Okay. So let me also write that. Again, sake of simplicity, P need not be a unit vector. Okay. Now, is this enough to describe every point? Now, how do you describe a point, for example, here? Okay, this is a point X. How do you describe this point? You join a line, right? And this is orthogonal, right? Do you agree? Now we can use them. usual math. What is the usual math? I want to look at this vector is orthogonal to P, right? So what is this vector? Or this vector, it doesn't matter which direction you pick, right? Both are.
X minus u.
U, right? So x minus u is orthogonal to P. You look at all x such that x minus u is orthogonal to P. That will describe all the points on this hyperplane, right? That's all. So what is this? This is x minus u transpose P equal to 0, right? Euclidean geometry and inner product is basically A transpose B. Then this is what you get. So what is the if you rewrite this, what do you get? X transpose P minus U transpose P equal to 0, right? Or I can write this as P transpose X equal to U transpose P. Well, U transpose P, I'll rename it. I'll call it as B. So it's B, right? In general, how do you write a hyperplane? It's A transpose X plus B equal to 0, or A transpose X equal to B, right? That's how you write your hyperplane. So let's write that as a definition, okay? A hyperplane is described by the following set. What is that? I'll just say hyperplane, which is all those points in Rn such that A transpose X equal to B. Okay, this is the hyperplane. Maybe I'll write A comma B here to describe the hyperplane, the parameters, right? A and B. Is that fine, everyone? Right, this is the hyperplane. Okay, fine. So suppose I give you 2 points. How do you say that I can squeeze in a hyperplane between the two, right? In other words, if I have a hyperplane, let's say this is your hyperplane, right? I should be able to say, I should be able to describe all the points above the hyperplane, right? So how do you do that? Huh? How do you do that? How do you do that? How do you describe all the points? So suppose I give you a line, right? How do you describe all the points above the line? How do you do that? How do you do that? How do you write all the points above the hyperplane and all the points below the hyperplane? I know how to write all the points at the plane, on the plane, right? That is given by this, easy. But above and below, right? Less than and greater, right? So let me write this as A comma B plus, which is set of all x belonging to Rn such that A transpose X is less than or equal to B, or maybe I'll say greater than or equal to B because it's plus, and I'll write A comma B minus as set of all points in Rn such that A transpose X is less than or equal to B, right? This is how I can describe. Now, going back to the previous question of this, right? Whether are the data points separable by a hyperplane? How do you write that? So let's formalize this whole thing. So, so what is the data set now? So data set will have, let's say D1. This is the first data set, which is X1, 1, Y1, 1, X2, 2, Y, okay, X1, 2, Y1, 2, and so on, X1N, Y1N, right? This is one set of data points. Maybe I'll, okay, so I don't think I need to write Y1, Y2 here. Okay, I'm sorry about this. So I need not label it, right? So the first data set corresponds to, let's say, spam. Then I don't need to write this, right? I'll just say X1, X, how do I, okay, X2, Xn. Okay, this is the first set of data points. What is the second set of data points? maybe I'll use Z. Okay, Z1, Z2, etc. Zn. So this is the second set of data points. I want to ensure that both are separable by hyperplane. What do you mean by that? So if D1 and D2 are separable by a hyperplane, then it means what? I should be able to have a hyperplane in which you look at all the points above it, right? That should contain D1, right? And all the points below it should contain D2, right? Then there exists AB such that H AB plus. So D1 should be here and AB minus should contain D2, right? That's it. D2 should be in the lower half, D1 should be in the upper half, and vice versa, whatever, depending on your naming convention, right? So that's what you mean by separable, right? Okay, well, of course, strictly speaking, there's some technicalities. Basically, what if it's on the hyperplane itself? We'll push it to one of them. Okay, so maybe I'll make that very precise here. Maybe I'll say strictly less than here. Okay, that means equal to is the hyperplane, right? HAB is the hyperplane. Less than B is minus, and greater than R. Okay, I think, I think both should be greater and less than, right? Equal to is all the points on the hyperplane. All the points above it should be greater than, strictly greater than. All the points below should be strictly less than, right? Okay. Now, of course, using this, the obvious question is whether there exists such an A and B, right? How do you find such A and B? Okay, that's a question that one can pose, right? You can say that whether I can pose this as an optimization problem. If so, what is the optimization problem, and how do you come up with such an optimization problem? So now, can you guess what should be the optimization problem? Wild guess, that's also fine. What should I do? What should I do? See, let's look at the constraint first. Okay, so what are the constraint we need? So problem, right? So let's look at constraint. What are the constraints that we should put? Suppose I give you A and B, right? And I say that it separates. So what should be the constraint? Huh? What should be the constraint? See, what can you say about A transpose X1? Should be less than or equal to B? True? Right? A transpose X2 should also be less than, okay, I'm sorry, it should be strictly less than B, right? Because it belongs to lower or upper, it doesn't matter. Okay, so this can belong to, I said D1 is contained in plus, right? So that means plus means what? My convention greater than, so I should change this. Okay, so it should be greater than. It's above the hyperplane, right? X1, X2 all belong to above the hyperplane. What else? This is one set of constraint, right? What is the other set of constraints? A transpose Z1, right? Z1 is less than B. A transpose Z2 is less than B, and so on. A transpose Xn, sorry, Zn is less than B, right? Now these are constraints, but what is it that what is the problem? So the problem is I have to find A and B, right? But this is just a constraint, right? These are called constraint set. I'll call it as constraint set. Okay, but this is fine, but what is the problem that you will solve? Typically, optimization should be maximization of some function subject to some set of constraints, right? So subject to is done now, right? So what should be the max or min or whatever you want to call it? Huh? How do you, what is the problem that you will solve? Hmm? What is the problem? Any guess? Do you think there is a unique solution or a unique separating hyperplane? No, right? There could be uncountably many. Forget about finite, right? There could be uncountably many, so many hyperplanes in between, right? Yeah. So, what is the problem that you will pose so that you will get at least recover one of them? Hmm? Hmm? Okay. Now let's go back. Again, it depends on the physics of the problem or the data that you have. Which is the best hyperplane? Whatever, quote unquote best. How do you come up with the best? Right, roughly, right? So suppose I take this and I keep moving. Okay, so I keep moving here. Do you think which one is better? The former, right? Black one. Do you think this is good? Still, see, these are all feasible solutions because it separates the two. But what might happen is, one of these data point right here, you would have observed this data point because of some noise, right? But in future, you might get data points belonging to this, which is somewhere here, right? Then you'll misclassify, right? On the other hand, what is the worst possible thing to happen? Something that passes through this, right? On the other hand, what is the worst possible thing that can happen? Something that passes through this, right? So, how do you find so-called best? See, separability is easy, right? So you should be able to find some AB. There are uncountably many ABs. One of them will work. But as an engineer, you have to find the best one, right? So that's where the objective comes into picture. So what do you mean by best here? Hmm? What do you mean by that? What do you mean by that? Of course, roughly you are right, but how do you pose that as a problem, right? Some function you have to say. The function should be such that it is moving closer to the other data point. The function should, if you are maximizing, then the function should go down, right? If you move to this side, also it should go down. Somewhere in between, you should have a minima, right? That's the best hyperplane you can find. So, how do you find that hyperplane? What do you think the solution is? What kind of hyperplane one should find, or what is the constraint on A and B, right? Any idea? Hmm? Huh?